We now prove the following theorem. For given epsilon, small enough, but smaller than some absolute constant. So if say C, okay, let's write it this way. So C is also small enough, then the following holds. If G is an epsilon, say D expander with a minimum degree LSD, then G contains K times C square root of D subdivision. So this will be sufficient for our purpose. If your ordinary graph G has average degree, say some large constant times E square, then what? You apply the previous theorem to find the sublinear expander whose average degree is almost same. This is epsilon D expander. And here you apply this lemma, then what? You get the case of like small c times large c, assuming large c is large, and that's like a lift T subdivision. So once you have this theorem, then you can get what we wanted. And we want to prove this. And we will consider 3 cases. And before that, let's M be this number, which is roughly the length of the path that we get from applying the previous lemma, which connects the two sets. So this will be the length of passes that we will take. And then let's choose some other constant so that like this holds. So we can assume that this is much smaller than this is much smaller than this, so this is capital K. Okay. Okay, actually there are more than 3 cases. Let's say case 0. So if n is smaller than kd, that means this is a dense graph. That means G has at least like 1 over k n square edge. 2. And for this, we can use the dependent random choice to find the one subdivision. One subdivision means that the ideal subdivision where every x is replaced with the path of length 2. Of complete graph on d over k square, say. Yeah. Then this is like c is much smaller than 1 over k, so this subdivision followed. So I will not prove this. So this was actually one of the homework problem. So you can do it for yourself as an exercise. So we assume n is bigger than kd. And let's say case 1. If there are C times square root of D vertices of degree at least a delta, which is D times M to the N. This is a case. In such a case, things become easy. So let U1 to U C times square root of D with the vertices of high degree. If you see, so where does this kind of number come from? Sorry. So this should be square root. Square root. Yeah. So of course the assuming that you have a subdivision of KC square root of D, then how many passes do you require? C square root of D choose 2, so roughly some C square over 2D many. And each path will have a length like M. So C squared, this is some constant. Essentially D times M vertices that is participating in the path. Those are the vertices you want to avoid. So whenever you want to use the previous connection lemma connecting two set, and this W will have roughly this size times some constant. So we want to make sure that if x1 and x2 are bigger than that, like dm squared is enough. Because 1 over m is smaller than 1/4 times log. 1/4 times log x. I mean, depending on this x, but x is bigger than dm. So this has one smaller exponent than size of x would be enough to avoid this and then connect. So here, that's where it comes from. So this is number much bigger than this, right? So if these vertices have a high degree, and you just take vertex and then its neighborhood, and this neighborhood has size at least d times m to the 10, that's already high enough so that no matter what w here, you can connect them as long as this is small. So you can see in this case, we greedily find a path one by one between them using the previous lemma, let's say connection lemma. At some point, we have at most c square root of d should true, so at most c square d passes of length at most m. So w be the set of those vertices in any of the paths. I mean, or the higher degree vertex, or the high degree vertex. I mean, the number of high degree vertex is small, so it's okay. That's something times square root of d. Then what? Then so if ui and uj are not connected yet, then let it be the neighborhoods of ui except the w, and let the x to be the neighborhood of uj except w, then what? W has size like at most this, which is smaller than rho of xi. So connection lemma is another path. And you keep repeat this until you get the desired copy of subdivision. So that's enough. So we assume that we had at most d like c times square root of d vertices of degree this. Then what we do? We delete those vertices to get the maximum degree condition. But what do we know? Original graph G has a minimum degree at least d over 2. And what? Between these two, they and the deleted ones are like c times square root of d. And then we know that d is large, then this is at least d over 3. The minimum degree condition is still fine. And also, how many we deleted? C times square root of d, which is smaller than, say, rho x divided by half for any x at least d. Our graph was what? Epsilon d expander. So all the sets of size at least d over 5 expands. D over 5 or d over 2? D over 2 expands. That's the definition. But for those, this is negligible. So this is roughly times x. This is roughly x over log square x. And this is like a square root of d. So this is small. So even if after deleting it, the graph is still the epsilon d expander after deletion. Technically, epsilon might become half epsilon, but let's just, okay, let's write half epsilon. And also this d become half d. But now we assume that the maximum degree is at most the d times m to the 10, and minimum degree is d over 3. Okay, so under this assumption, we assume two things. So let's say case 2. So d is at least log n to the 100. So in this case, how do we do it? So this previous case was extremely good because you have already lots of vertices with high degree. And then this was large enough to connect. While doing that, you wanted to avoid this part. So you want to avoid, when you are connecting these two, you want to avoid what? Other paths as well as the high degree vertices. The number of high degree vertices is also small enough so that avoiding them is good enough. And yeah, so that was the case. But now, this gives us some idea that we want to find some structure like this. So instead of this is just star, right? Instead of star, what if we have some subgraph whose exterior is large so that we can connect them while avoiding small part? And this interior is small so that while connecting them, we can avoid the interior of some other parts. That's our motivation. And then based on that, we define the following. We say that the H1, H2 hop is a rooted tree with height 2. That this is how you look like. It says degree H1, and then it says degree H2. I mean, let's say has H2 descendant, child children. So that's H1, H2 hop. And let's say we say H0, H1, H2, H3 unit is a tree consisting of a V core vertex and what? Internally, vertex disjoint passes, I mean, sharing only at E of length and most H3. And how many passes? H0 such passes. And then each of them is connecting disjoint H1, H2 unit, a hop. So this is a unit. And then we say the leaves here are exterior. And remaining is interior. And we say that this part is core. I mean center, not core. Center. And this interior part, which is not in the center, is middle vertex. Let's call it this way. So it's clear what each term means, right? Okay. This will replace the star that we saw before. So this part is exterior, so it will be large enough so that we can connect them while avoiding centers of other parts and then previously built path. And center is small enough so that you can avoid it while obtaining the paths using the connection lemma. Yeah, and these middle parts have a size comparable to the vertices in the number of in the paths, so that I mean, you will later see that we will make sure that not many vertices in the middle vertices participating in the paths. The paths completely avoid the centers, and exterior is too large, so we can connect them. Then this has a size, I mean, in a right size, so that some of them might be used by other paths, but not too many. So in our case, we have like interior and then exterior. When these stars have large degree, so this is a similar situation. So one thing is that one thing is that from our choice, I mean, this is always very smaller than, say, n over large constant. Say this. Why? M is what? Log cube 15n over d. 2 over epsilon, right? So we don't know how these two relate, but we know that this is bigger than k. Then what? T m to the 100 is like 2 to the 100, epsilon to the 100. You can write n over t, hence log 300, like 15n over d. So you have n over d and n over d here. So writing n over d as x, log 300x divided by x. If x is large enough, it is going to 0. So this goes to 0 if this is large. So when this is bigger than k, this is like almost 1 over k to the 0.9. Then the k is much smaller, much bigger than 1 over epsilon. So this is smaller. So one thing we know is that no matter, we don't know how G and N are related except this one thing, but we already know that this is a negligible portion of everything. Then what? Now we want to show that we can build many units in a way that their interiors are disjoint. Their exterior intersecting each other is fine, but we ought to make sure that their interiors are disjoint. For that, we first claim that we can get many hubs. So we know that any graph, okay, let's say if we delete, let's write it this way, and most say d times m to the 50 vertices from the G, it still contains C square root of D, C square root of D hub. So this is easy. Why? You deleted that many paths, vertices. And then each vertex has what? At most D times M to the 10. So we assume that every vertex has degree at most D times M to the 10. So we have deleted, give me a moment. Yeah, this many edges. But in the original graph, how many edges were there? D times N edges. And this is bigger than what? D squared times M to the 100. So after deleting this, still you haven't deleted half of this. So at least half edges of G are still there. It's not deleted. Then in that graph, the average degree is at least half. So G, the graph after the deletion, still has average degree at least d over 2. Then what we know is that it contains a subgraph with minimum degree at least d over 4. Then in here you just take any one vertex, and then you take c times square root of d neighbor, and then here again c times square root of d neighbor, in a way that all these vertices are different. I mean, up to here, the participating vertices are like at most this much, and then this vertex has at least d over 4 neighbor, so you can choose it which are different from here. So you get the H1, I mean, is hop C times square root of D, comma C times square root of D hop. So now what? Now we build the unit. So iteratively build unit. So 2 times C square root of D, comma M square, 2 times C square root of D, comma 2M units. U1, U2, up until 2, we get 2 times C square root of D. In a way that for the interior are pairwise disjoint. So once we built I of them, which is almost 2 times C times square root of D, and the set W of their interior vertices as guys one. And most, how many do you have? So each one give you 2 times C square root of D, and then this length is like M 2M, and here the is expanded by M square, and then 2C square root of D. So up to here, you get 2 times C square root of D times 2M plus M square. And the number of units is this, so at most what? Like 10 times D M square. So C is a small number, so we ignore. And this is smaller than N over like M to the 50. So instead of that, you can even write N over 1 to the 50, which is, yeah. So N over M to the 50. Then here, this is N over M to the 50. Then you have deleted much far less than Dn edges. So the previous thing holds. So yeah, maybe yeah, either one is fine. This or this. So this is smaller than D times M to the 50. So after deleting this, so she still have a hop. So hence G minus W still has the and we find one, and then we again add it to W and then find another one. We keep do that as we iteratively find the C square root of D, comma C square root of D hops H1 to HM cube, and 2M square or C square root of D hops H prime 1 to H prime M cube square root of D. So how do you find this? So this number is smaller than this, right? So once you find this, you delete them, and then you can obtain this smaller hop. So you keep do that until you get all this hop. Indeed, I mean, you can just, again, compute the number of vertices here that you have to add to W to get the next one. Then you will see that this is fine. And then what do? You draw this hop. So H1, H2, HM cube. And here, H1 prime, H2 prime, and HM cube square root of D prime. So you can see that here, this is smaller hop, but there are many. This is bigger hop, there are smaller number. And how do you find the unit? You want to find the passes that connects many of them, and then that will give us unit. But now we iteratively build passes between them. You can see that this exterior set and this exterior set are large, so that you can add passes. In fact, you can, let's say you have already found some passes here, and say here, and say here. And what you do is that once you found this path, then you forget this. You forget this, and you forget this, and then still there are remaining things. So here you don't forget it. But you add vertices on this path to the W, and you no longer use this hub. And then you add this, and then you no longer use this hub. You add this, and you no longer use this hub. And you do that until when? Until you find one of that that's connected to enough number of hubs so that this number is like this number, then you will get this unit. So assume it's not done yet. So assume we have built a vertex disjoint passes between hi and some h prime j. If we find hi that is connected to at least c square root of d hubs hj prime, then if there's another unit as desired. So remember that we have already built some unit, and then we put the integer of them in W. Otherwise, what? Out of m cube square root of d hubs on the right side, each m cube of them is connected to less than 2 times c times square root of d of them. So this one is much smaller, half times this. So half of these are still here. So these are kicked out, these are kicked out, these are kicked out, but the unkicked out one is still half of h prime j are not connected to any path. And let x1 be the union of exterior of those things. So let's say you have another one here, and these are x1. And let x2 be the set of exteriors of h1 So each h1 has what? this degree is 2 times c, 4 times c square root of d, and what is connected to and most CD. So CD of them are already connected. And then you forget them and then you leave the remaining. Then, I mean, that of the exterior vertices. E of HI, whose parent is not used by any passes, any of the previously built passes. So there are n cube of them, and each of them, out of 4c square root of d, 3c square root of d are still there. Sorry, this is 2. Yeah. So out of 4, 2 of them are still there. And then for each of them, it's expanding by like give me a moment. It should be given 4 and 4. And 4c square root of d. So that's size of x2. It's at least 6 months. Which is like AC squared dm cube. Okay, and then this size what? At least this of them are not connected. Then you expand 4c d times 4c square root of d. It's like half m cubed square root of d. So both of them have size like each xi has size at least like c squared dm cube, while the vertices we have to avoid. The W contains and most, as we saw before, we added the vertices from previously built unit, interior vertices of previously built unit, which has 10 dm square vertices from the interiors of previously built unit. And also the previously we add the vertices from previously built passes. And how many passes have we built? So here. So each one is connected to less than 2 times CD. So CD hubs and this. And then you multiply 2m as the length of the passes. So 2m times m cubed times c times square root of d, which is like 2c m4 square root of d. But here you have d and here square root of d, and then you assume that the d is at least log to the 100. That means this one is bigger. So in total, w now has almost 20 times the m square. And if you see, you have same d, but the m has higher power. So this is smaller than like rho of x times x 1/4, or x bigger than say this. So you can use connection lemma, provides a path from x1 to x2, avoiding W. Okay, so this shows that we can find c square root of d comma m squared 2c square root of d 2m units. You want to use 2d that are interior disjoint, very interior than pairwise disjoint. So now what you have this unit. Its exterior may not be disjoint. Here. Now what? We connect them one by one, find the passes. And once we find passes, now this will be our path. While doing that, you want to make sure that your path does not intersect the center. What I mean by path is green part. This green part does not intersect with any center. Middle vertex, it may be intersect, but as we have collected 2c square root of d of them, if some middle vertices are too much occupied, we can throw some of them. We are opposed that. So how do we do it? We greedily, one by one, we connect UI and UJ one by one. Moreover, exterior of UI one by one using connection lemma. While doing that, W is the set of vertices in the previously built path. And the center of unit. And W is always what? Guys, at most 2c square root of d choose 2. And each path they have rank at most 6m. And there are say this many interior vertices are like this times the m, the central vertex. And then there are like c square root of d of them. So altogether, you can show that it is like 100 times c square dm. So W is always almost this number of vertices. And while you're doing that, we make sure that our new path will never intersect W. Then the new path that we take, it might intersect middle vertex of some unit. And what we do is if at least, say, 100 times c times square root of dm middle vertices of some uj are used, and we throw away. We throw uj away. So that's ruined, so we will not use it anymore. But we can make sure that we don't throw away too much, because we only throw away if that many vertices in the middle vertices are used. But the middle vertex of all the units are disjoint. And then in total, there are this many vertices in the passes. So 100 c squared dm divided by 100 c squared dm is smaller than c times square d of the units. So, and most, if many units are thrown away until the end. So at least c square root of d, so we collected 2 times square root of d times c many units. So half of them will survive. So these units are, left. Among the left one, you choose 2 of them which are not connected, and then you connect. While you're doing that, let's say you have if ui and uj are not thrown away, they're not discarded, then what? Then it has at least how many middle vertices are not occupied? Like 2c square root of the m square middle out of middle vertices. 100c square root of the m, less than that many are occupied. So at least c times square root of the m square middle vertices are not in W. And then let them be AF for each F in I and J. Then what do you know? You consider the neighborhood of this, external neighborhood of this, and then forget the W. Then what do you know? In this interior, it's one of them. So this and these are disjoint. This and these are disjoint. These hubs are all disjoint. This may be intersect with this. So this vertex may be same vertex with this. But in here, these are all disjoint. So this neighbor has sides at least what? Depending on the degree here, 2c square root of d times this c square root of dm square, which is 2 this c square dm square, which is, again, here, m exponent is 1, exponent is 2. So, connection lemma is a path from here, say this is I, to n aj w, avoiding w. So you can do that until you find the desired k sub c square root of d subdivision. Okay, so that's concluding the proof. And last case is when d is extremely small. So log to the 100n. So this case I will not explain in too much detail. So basically what you do is in here, again, you assume that you have bounded maximum degree. And then d is very small. That means if you take a one vertex and then you take, say, its ball around it with, say, r is like log n over log n. And every time it expands by m mod d, one vertex is first layer is m mod log to the 100, second layer is m mod log to the 200, etc. For such a choice, this one is small, still small, m mod n to the 0.1. And you delete it, and then you take another one, you delete it, And what you can do is you can find many points, at least square root of these points which are far away. The distance between them is at least they are. Then what you do is we want to again gridly connect them. But now the issue is what? If you have W that you want to avoid, which are like vertices of the paths that you previously built, then they have size like D times again M, or yeah, D times M times some constant. But this is too big. Now you want to grow this, but it's growing so slowly, so that it's difficult to find a set which is much bigger than W. But what you can do is that because they are far away, you can first make sure that these passes is far away from here. So if you grow this, say, log n to the 5 times, it will never see vertices from here. It will see some vertices from this path. But this path, you will never see because they are far away. So you can build the path in such a way. Then you don't have to avoid entire W. You only have to avoid W in here, in those paths incident with this vertex, and close until you expand this many times. Moreover, what you can show is that this beginning portion of these passes are something called consecutive shortest path. Meaning that in here, this first path is shortest path between these two. And then once you delete these vertices, then your second path is shortest path between these two vertices. And your third path is shortest between these two paths after deleting these vertices. If you know this, then each of these vertex, each of these paths intersect with this layer at most one vertex. If it intersects with two of these, then this is not shortest path. You can skip this vertex and then directly go, which is contradiction. So from here, what you can show is that this layer is only square root of D. This layer is only square root of D. This layer is only square root of D. While every time it expands like D, and then the first time it expands like this, and then after that you expand like 1 plus rho x times x, and then the addition is like x over log x, so which is like D over log x, which is bigger than square root of D. So what you can show is that this many times you can expand. While you're doing that, the W being large is no problem. The only possibility that some vertex of W is in your way are here, but because these are the consecutive shortest paths, that's very minimal effect that you will get. So you will still be able to expand them many times. And after that many times, you make sure that this set has size like D times M cube, or D square times M cube. Not D square, D times M square. Actually, D and M are on the same order. So this is so big now that you can actually avoid this W. In the same way you do that, and then this becomes so big now, then you can connect them. Once you connect that, and then you add the shortest path between here and here again, so that this forms another consecutive shortest path. So next iteration is okay. So that's roughly the idea of the last case. And yeah, there are certain more research after this. So there are like you have what? Average degree D, then you get the K sub C square root of D subdivision. And natural question is that when is it tight? So before we showed that this complete graph, this was tight, but if you exclude that, then can you get better? One conjecture was that if your graph is K2 free, the Mather's conjecture, then this is far from being this dense bipartite graph, then can you get the much bigger subdivision? Subdivision of size C times D. So this is proved by Liu and Montgomery in 2017, and they used the sublinear expander. The concept of hubs and units are developed by them. The original proof of Komros and Temerity are a bit different, but what I presented is based on their proof on this. And yeah, there are more research on what kind of condition give you better like subdivision. And yeah, I will not talk about it that much, but there is an excellent survey by Letzer in 2024. I mean, there is a survey on sublinear expander. There are lots of interesting results that prove by using this sublinear expander theory. Okay, I think I was a bit too fast in explaining things, but I hope, I mean, it was okay for you to understand that. Okay, thank you for listening, and I will see you in next time then.